consideration. Oh, recording in progress. Let's remove that. Sorry for that interruption. So why are we talking about that today? So I think most of us are aware that the severity of the threat which internal corrosion will play to the integrity of your equipment. Examples in the hydrocarbon industry are obviously pipelines and piping, your tanks and vessels. And we know that if you fail to manage the threats from internal corrosion, you can see catastrophic failures. Being able to monitor the rates of corrosion and classify their severity is a key part to ensuring that the safety is maintained and you have continued and reliable operation of your assets. What I'm going to talk about today is obviously selecting the most appropriate location for your corrosion monitoring device, and how that's critical to the accuracy of how you detect your potential internal corrosion mechanisms, and also how you can quantify that as a corrosion rate. So I'll touch on 4 major factors. These are not exclusive, but these are the ones that, from my experience, are generally focused on. And these are more towards production piping and also pipelines. That is where the bulk of my career has been spent. I'm not super experienced in any way on tanks or vessels. So I'll cover process conditions, possible corrosion mechanisms, how you can mitigate your corrosion, internal corrosion, and very crucially, the accessibility of the chosen monitoring location. I'll also do a section at the end, towards the end of the presentation, where I'll give a fairly high-level overview of, traditional and available monitoring techniques, which most people who deal with these things or touch this subject would be familiar with, primarily electrical resistance or ER probes and corrosion coupons, and how they can be used to effectively monitor your corrosion. So the conditions within your systems can obviously have an impact on the rates of internal corrosion you may see. Some environments may, promote the corrosion of your metallic materials, and some environments may inhibit it. Broadly speaking, corrosion is considered, the process of where metals are degraded by an electrochemical reaction within their environment. And some of these are the more common factors that can contribute to this. I have to pause for 2 seconds because I have to go and silence the alarm in my building. Apologies. Okay, apologies about that. It's the middle of the night and the office alarm decided to activate itself. So I had to run down the stairs and deactivate it. So I will continue. So we can focus on some of the more common factors that might contribute to corrosion, those will include, the makeup of the metal which is used, the composition of any fluids that may contact the metal, including pH. Temperature is obviously a very big factor. And then do you have, additional corrosive agents or contaminants within the system that may promote corrosion? Generally speaking, in a piping system where you have fluid present, that can really affect your corrosion rate. It's important to understand how that can affect pipeline corrosion, and why it's important to select, proper materials, as well as implementing an effective corrosion mitigation method or a mitigation strategy, for example. So these are some examples of factors which I would consider important in relation to internal corrosion within piping and how it can be influenced by process conditions. So the first one would be fluid composition. So if you have fluid within the system which is potentially contacting with metal, that the makeup of that fluid can really influence your rates. Some common examples would be the presence of, some fairly common dissolved gases within a hydrocarbon system. Oxygen, no one really usually wants to see that. You have hydrogen sulfide when you have sour production, and also carbon dioxide. Also the possibility for scales or bacteria. These can also influence under certain conditions. pH, which anyone who's done any of the formerly NACE and now AMP training courses, there's a big section on that within at least 2 of the courses on how we measure pH and why. Because obviously, it's through many years of measuring and tracking it, it's been identified, where you have low pH in a fluid, where you have acidic solutions, that can for sure increase the rate of corrosion. On the high pH fluid side, we have maybe caustic solutions. There's potential in certain extents that could be reduced, but it can also result in additional operational problems. Temperature, this is one of the most common conversations I have with a customer, where they may see, accelerated rates or higher than expected rates, or rates that, have taken a very rapid jump from one set of data to the next, especially in carbon steel systems, which, are probably by far the most prevalent within the industry. The gradient of the temperature is also, you can have different rates along the length of the pipe. And the most common fact that I'll share with a customer would be, if you already have an active corrosion mechanism, so you have internal corrosion, existing in your system, and you, for whatever requirement, have increased your operational temperature. If you increase it by 10 degrees C, it's considered that could have an effect where you double your rates. So if you, worst case scenario, you already have a very severe rate, that would be, very bad situation. Contaminants, so, very commonly things like salts or chloride, sulfides. When these are present, within the fluid, you can see, for example, situations where you have the chloride ions, they can penetrate your oxide layers, and almost initiate a corrosion cell. On the flow rate side, very common to monitor and measure your flows. Turbulent flow, that's generally considered to cause an increased rate of corrosion. You have more mixing of fluids and gases and other material, and that can increase the opportunity for a chemical reaction. And also there's the higher the flow rate, generally speaking, there's more potential for erosion of the surface. Most people's enemy within a system would be oxygen. Oxygen in the fluid, that can cause iron oxide, that can react with water in the fluid. You can have the formation of hydroxide ions. This leads to, much more accelerated corrosion. Microbial activity, so the presence of your microbes, or like what we generally call them here, would be bugs. And people like to talk about bug counts and bug treatments. You can have the formation of these colonies on the pipe wall. So if they shift from planktonic, which is free flowing within the system, to a sessile, which is where they attach to the pipe wall, you can have these situations where you have rapid localized or pitting corrosion due to the environment that these colonies create. So moving on to mechanisms. So what are these are your more common mechanisms that can cause internal corrosion. So one of the first ones that we usually talk about anyway, standard, would be, uniform or general corrosion. So this would be where, you have almost, hence the name uniform, but you have corrosion occurring in a kind of uniform pattern over time. Usually caused, well, not usually, but fairly commonly caused by, exposure to an aggressive fluid or something that's acidic or alkaline. You have a anodic area that moves, within the surface instead of staying in one spot. Galvanic corrosion, so this is something that everyone has to be very aware of, and we have different potential for dissimilar metals contacting each other, and where you have that electrolyte, commonly a fluid. One of the materials will be the anode, which will corrode, because the other will be the cathode, and that one is usually protected from corrosion. Can be very damaging to the pipe if the anodic area is small and the cathode is large. That can also cause some fairly accelerated localized corrosion. Crevice corrosion, not usually an easy one to explain or capture, or even mitigate. Easiest way to think of it is where, you have a stagnant environment and the geometry of the environment, like a small gap, or, as the name suggests, a crevice, between a metal surface and another material, which could be, your like a gasket and a flange, or an insulation. The environment can be very conductive to corrosion. There's potential for an acidic or an alkaline environment, in the crevice, which can then also promote localized corrosion. Not, in my experience, generally considered the more, high risk of the mechanisms, but one that definitely needs to be monitored and measured. Pitting or localized corrosion. So, throughout my career, this has been the one that customers have really had to battle the most aggressively. So very simply, you know, you have a small area within the surface that becomes an anodic area, and you see that pit or that localized, you know, corrosion start to form. This means that the rest of the pipe is acting as a cathode. So you have a very small anode and a very large cathode. So understanding, you know, a corrosion cell and how corrosion works, that's obviously a very bad scenario. In the industries where I've worked, in the different regions where I've worked, which is, you know, quite a few, pitting or localized corrosion is usually the most common cause of failure in the pipe wall from internal corrosion. Very aggressive, and once it starts or detected, it's very important to combat it as aggressively as possible. Stress corrosion cracking, it's not one I deal with very often, but you know, we do have some systems we manage here that we monitor for it. And basically, where you have stress on your pipe or piping, and there's a corrosive environment, you can see that cracking within the structure, and you have a very rapid failure, and it can happen very quickly because it doesn't need a lot of corrosion to cause that. Next one would be MIC, or microbially, very hard to pronounce as a Scotsman, but microbially influenced corrosion. So hence why I'll call it MIC. It sounds like an Irishman. So MIC, that occurs when you have these bacteria, which I mentioned previously, which go from being, you know, planktonic, which is free flowing within the system, to a sessile environment where they adhere to the pipe wall, especially if there's moisture. These microorganisms or bugs, you know, they have a metabolic byproduct. Usually, in an example, that would be where we have organic acids. So these colonies, once they form, can very rapidly lead to pitting or, you know, localized corrosion. So now that we understand that, we have to mitigate these somehow, because, you know, we know that our system is influencing corrosion. We know we have an active internal corrosion mechanism, or the potential at least for one. So how do we manage that? Most common, in my experience, and not in every market, but generally speaking, would be your inhibitors, you know. So where you add chemical into the system to try and reduce the corrosion rate. You know, there's many different types of corrosion inhibitors using different reactions and bases of their chemistry to work, and they have to usually be very, you know, fairly fine-tuned to the individual system itself, because you're trying to affect that chemistry. But they rudimentally, they'll form a protective film or a layer on the internal surface of the pipe, which is designed to, you know, prevent the initiation of corrosion mechanisms, or if you have, you know, an existing mechanism, somewhat, you know, reduce the risk from that. Second most common would be, you know, what's the industry term of pigging or mechanical cleaning. So where you have a device that's sized for the system in use, and you insert it into your piping or pipeline, and it travels along the distance of the pipe. You know, it's back pressured behind it, and it pushes in front of it out into a trap, you know, fluids and solids or debris, you know, trying to rid those influencers from your system. And also, like, especially in the piping and, well, the pipeline market within Canada, fairly common to use a pig also to deploy your chemicals. So you'll have one, you know, what's termed as a you know, a cleaning pig, fairly aggressive pig up front, and then behind it you'll have a secondary device that will deploy a batch film to the pipe. Few other methods include, you know, when things you can control effectively would be, you know, your flow control. That's something that, you know, to an extent can be controlled, and we know as an influencer. Up front, you know, like very carefully engineering your system, and, you know, material selection would be a part of that. You know, there's a lot goes into the science of metallurgy, and, you know, and sometimes there's, you know, there's obviously a financial element to it as well. And then, you know, growing in stature more and more now as systems become older or are expected to last longer, you'll have, you know, internal linings or coatings. So accessibility. So when we position the device or select the location, you know, very much a focus on it being representative. So you want the device to experience and see what, you know, the pipe itself sees. So normal production, upsets, and your mitigation methods. But it's also very important when selecting that consider the accessibility of the equipment and the people required to, you know, install and retrieve the device. I'll cover that in the next few slides in a bit more detail, but very commonly internal corrosion monitoring devices are placed within the flow and removed for either analysis or replacement during normal operations. So you get the exposure of the normal process environment, and you don't have to shut that down, depressurize vent to access the device. Very recently, the standard AMP standard, which is still called NACE, SP0075, is now 2023. It's usually reviewed and revised every 5 years. I believe it was released sometime in February. One of the new considerations within it was more of a focus on accessibility for these devices, and making, you know, some good, you know, effectively common sense decisions. So what do we consider? So we're considering the type of equipment that's being utilized, vertical and radial clearances that the equipment may need to install and service it safely. You know, the actual physical location itself, the environment, you know, is it at height, and what are your access and egress possibilities? The orientation of the device, you know, like, are you positioning the access point to deliver the device in line on the top, the side, or the bottom? Is it a newly engineered system where you can carte blanche specify what type of system you want to put in there? Or more commonly, are you retrofitting? And are you trying to make some, you know, piping construction changes or other mechanical changes, you know, reorientating other equipment, you know, cable trays or other sensors? Or do you need to construct some access point itself? You know, the 6 o'clock one may require, you know, access below that wasn't previously considered. On the top of the side may need you to add a platform or something to give, you know, intermittent access to location. And then, you know, lastly, design parameters of the system. Like, the two that we mainly focus on would be, you know, your design and operational pressure and temperatures. So we're going to pull it all together. So we've reviewed what, how process conditions can influence internal corrosion, the possible mechanisms, mitigation methods, location accessibility. Also, that, historical information, what is available, or, what, you have, or, any, potential data you can piece together. That's also, something that would come into the consideration. When we use this information, because, we talked about it before, where we want to make sure the location selected is representative, and the device will give us, data that we can use for effective decisions, and how we are, measuring and mitigating that rate of internal corrosion, and possibly the type of mitigation methods, are they effective? So in a scenario where our client has a low temperature laminar flow liquid line with, expected to see organic solids materials, potential for microbial activity, their system is carbon steel, they are mitigating that by, continuous inhibitor injection. There's a location at the end of the line before joint separation, and there's sufficient clearance for both top of the line and bottom of the line monitoring. So when you pull all that together, where do you position it? So my recommendation would usually be, in that environment, bottom of the line, monitoring would be preferred. But as you have that spot and you have that potential, why not add a top of the line as well, in case there's a potential in the future to, for the need to measure, top of the line corrosion. So we'll move on to some of the common systems. So first off, as I alluded to earlier, generally globally best practice on these devices would, you would have an ability to install and retrieve them. That means you can do this without waiting for, a turnaround or a shutdown, which can be relatively infrequent. And, you can select your own monitoring interval and adjust it based on the data you see. There's two common systems within the industry. So the most common would be the high pressure, access fitting. You can have those rated up to 10,000 PSI if you have an API flange. They do require, the retriever tools, and people who can use them safely. There's a very high level of, options on them for materials and the connection types. Most common connection type globally would be the flare weld. After that would be a flange, and not many people would disagree that that's the industry standard. There will be some, but not many. On what's called the lower pressure retractable, although if you consider 2000 PSI low pressure, then that's brave. But those are the ones we manufacture rated to 2000 PSI. These are installed using an existing valve that must be in situ on the line. They're versatile because you can change the end on the coupon, on the rod itself, very easily to change your coupon design. And and you can move them from point to point. You can't like move a flare weld very easily, flare weld access fitting very easily. And at low pressure, in low 100 poundage, they can be done safely with hand tools. So we have mechanical and electronic techniques and mechanical methods. By far and away, the most common would be the corrosion coupon. Full name would be a weight loss corrosion coupon. There are many different types available. The intention of the coupon is that it would be made from the same or a similar material as the piping. And, you know, as talked about a few times when we've discussed representative, that it would be in the same environment that, you know, the pipe wall would see. So it would see, you know, normal production upsets, and also experience the mitigation method that's being used. You can calculate a corrosion rate and a pitting rate from these. This is done by a physical inspection and measurement. So the physical weight loss of the coupon is used to calculate the corrosion rate, and we measure localized or pits to then use that to, you know, calculate a pitting rate. Two main types, non-intrusive and intrusive. Just like they sound, the non-intrusive coupon is generally known in the industry as a flush coupon. You may also see a trap coupon sit beneath it. When you add an access fit into a system, especially when you add a flange type, you do create that dead spot where, you know, some of the things we discussed about how the system influences corrosion, those can settle in those traps. So that coupon is positioned in there to measure that almost like worst case scenario. They sit flush with the pipe wall. That's very important because that means you can peg past the location. There's no danger of the peg, you know, damaging, being hung up or stuck in the system caused by the coupon. Very handy tool for swabbing. So you can take samples for solids, you know, and fluids, and then most commonly, like, the fluids would be used for bacteria measurement, and definitely the industry standard when you have a bottom of the line access location. The intrusive, or as most people call it, a strip. These are available, you know, as multi-phase ladders. So you can see in that image where you have three positioned in different parts of the flow. Most commonly it would be a pair mounted, you know, in the electrolyte or fluid. So in a system with a high, you know, for example, water percentage, they may sit in the middle of the flow. More commonly, they'll come in from the top and be positioned in the bottom section. So when you have that top of the line location, that's generally what's specified. Few other ones, less common, but, you know, still can provide valuable data. So a scale, or in some regions they call it a wax coupon. There's no magic calculation to them. It's a physical indicator if you have scale or wax buildup in piping. So instead of the bladed style intrusive coupon we've seen before on the strip, where you mount two and the blade end faces the flow, the holes in that coupon, you can see they're face the flow, and you're trying to simulate that pressure differential. Bioprobes, so that's a non-mechanical, mean it's not electronic. You have these studs that you can see in the image. You position that the same way you would a coupon. I mean, you can position it in the center of the line as well if you want to try and catch free flowing or planktonic, but in my experience, that the wall is, you know, a more representative method. And you'll remove one of those studs per visit, and you take that stud, and obviously the fluid buildup on that can then be, you know, analyzed, and there's many different techniques for that. The bottom one there is a sacrificial probe. So that's basically a probe that's designed to fail. It's an exterior tube over an interior, and there's a small gap. And then what happens when you have corrosion, erosion, I mean, also you can have straight erosion, that tube fails, and then pressure passes through the body of the probe to a device which will alert the client that has happened. That can be as basic as a pressure gauge, which is just manually checked by operations, or you can go all the way to a pressure differential switch, which will alarm in for example, a controller. On the electronic side, so the one that I deal with the most would be your ER probe. Very simply, there's a measuring element which is exposed into the environment, and behind that, within the body of the probe, there's an unexposed reference element. And when we see that change in resistance, we can use that based on the geometry of the element itself to calculate physical metal loss. That can then be trended over time and analyzed, and also you can use those points to calculate a corrosion rate. So they will give you much more rapid data density than a coupon, but there is some significantly more complexity into interpreting the data. Again, like a coupon, you have a non-intrusive and intrusive. The flush for the non-intrusive type of probe, you can see metal gain on these probes, where there's that people and some people still do see that as a weakness, but you can see you have conductive scale build up on the element, because it's the element can't regrow, like it's already begun to corrode. And what we tend to watch for production here is very sour. We tend to watch for what happens when that scale is removed by the process environment, and what kind of rates we see following it. Again, it lets you sit flush with the pipe wall so you can peg and operate normally. Again, you can swab it if you choose to retrieve it. And another one that was, same as the coupon, is the industry standard for the 6 o'clock. The intrusive, some people call it tubular. We tend to refer to it as a cylindrical. Those, similar to a strip coupon, you're trying to chase the electrolyte with those, generally coming in from top of the line to the bottom or the center. They will prevent you pigging the line because they're an obstruction, and they can suffer from velocity issues. So it can be sometimes you may be required to put a shield on it to try and reduce that effect, but that can have a counter effect on the accuracy of the data that you're measuring. And how do we take those readings from those ER probes? So again, two main common types. You need to give power to the probe, and you need to store the data. So the data logger, that's like a standalone unit that you have to physically go to. The one we produce, you can store 50,000 data points. It is a standalone unit, so you have to physically go to it. There's obviously some advantages to that, but a lot of the time in remote facilities, that can be a disadvantage. There's a limitation with a battery, which means if you don't go very frequently, you may lose the battery, and then you lose data. The transmitters come in a whole variety of types and designs, mainly based on, are they wired or wireless, and then how are they handing that data off or communicating. Most commonly to your DCS, you'll have 420 milliamp, which is one of the first ones ever conceived. More recently, in the last 20-25 years, we've gone towards HART protocols, more recently ISA, and then you have Modbus, and then very commonly RS485. There are cellular and solar options for those, where you have, again, remote access, power, comms issues. And the data from these days, like, we can upload those to a cloud server, and we can have a front end interface that can be completely bespoke. So, you can use that you could basically sit at your desk in town in KL and dial in to the server and see what your probe offshore Murray is telling you. So I think at 46 minutes, that is me. So I will stop sharing that for now. I'll bring it back up if anyone wants to look at specific.
All right, thank you, Tommy, for the sharing. This is the Q&A session now. You can post your question in the meeting chat. At this moment, we have a question from Fahim Afridi. Tommy, he's asking, the question is there any specific position of the monitoring location based on the type of corrosion?
Sorry, I made the classic Zoom mistake where I muted myself and forgot. Yes and no. You want to be, following the kind of thought process that I showed in the presentation, where you want to look at first, what are the potential influencers? Now, from that, you can identify, you have electrolyte, you have, laminar flow. You're very likely going to detect the corrosion in the 6 o'clock position, the bottom of the line. But difficult to completely predict that, like you can model the system to eternity, but until you actually start production and flowing, you have to be aware that things can change and you may have to adapt to the system. So yes, but you kind of have to follow that thought process that I was trying to kind of like outline. Does that make sense?
Fahim, does Tommy answer the question? Do we have any more questions for Tommy?
Who thinks I sound like Conor McGregor? He's from Ireland, man. I'm from Scotland. That's a good one. I like that. Yeah, and apologies for the alarm activating. Like, it's almost 2 a.m, so I wasn't quite sure what it was going to do, but it just started to set itself automatically. But it shouldn't do it again. If it does, I'll have to go and deactivate it. But so does anyone else have any questions? Like, anyone have any different points of view or different experiences they'd like to share? Those are always very valuable in this kind of environment. You guys know your systems better than I ever could.
Yes, coach. Actually, just a doubt. Can we get the PPT for our future reference as I posted in the text box?
Sorry, you'll have to repeat that. I didn't catch that. The volume was too quiet.
Yeah. Can we get this presentation slide for our future reference? That would be
I can give you a PDF copy of it. Like, I'm not usually allowed to distribute like the native file, but I can give the team. I think I already actually gave Demi from AMP a PDF version, so I'm happy if they want to distribute that to anybody that wants it.
Yeah. Thank you very much.
Yeah,
I will get it from the organizers.
No problem. Yeah, they have it. If they don't have the copy, Demi can let me know and I'll resupply it.
Yep. Thank you very much.
Tommy, we have another question from Budi Yaya. His question is, can we use different handheld brands for different LRP, ERP brands?
That's an excellent question. I've got a similar answer, yes and no. Yes, you can, but it depends. So ER probes, much simpler. They are very much all of the same principle of design. Some manufacturers may tweak the pin configuration, but you know, I can tell you how to cross that over. You can just change the adapter you use, but very commonly the most common global brands for connecting to ER probes, they're the same configuration. There's some technologies that, you know, there's a word which I hate, which is high resolution ER, or a phrase, not a word. And those technologies are kind of like an iPhone, they're fairly locked. But you know, what you call standard ER probe design, pretty much every meter or data logger can be connected to that fairly easily. LPR is a little different. The LPR measurement, the surface area of the electrodes is crucial to how it you know, I mean, it's effectively a theoretical measurement. Some people on here might argue that with me, but I don't usually use LPR in any system that has, you know, something that could foul it, or hydrocarbon mainly. Those are different because different manufacturers have different electrode styles and different surface areas. And you have 2 electrode styles and 3 electrode styles. So they can be a little challenging in terms of interchangeability, or like in the old days when I used to, you know, go down to Murray and meet with the teams down there, like we would talk about mix and match a lot. And you can mix and match the mechanical stuff usually fairly simply, but the electronic stuff's a little more complicated. But ER, you know, I can definitely show you how to do that if you're having problems. LPR is trickier. You can do it with LPR, but it's dependent on if it's a 2 electrode or a 3 electrode probe, and if you have, and who made it basically, because there's a difference in those surface areas, and that is a factor on how it spits out its corrosion rates and pitting tendencies. Does that make sense?
Budi has a follow-up question. His question is, what is the reason for the negative readings for probe?
Yeah, that's a great question. So what I was explaining when I was talking about the ER probe, and I talked about metal gain. So, you know, you start from you start from like effectively a 0 mils position on your probe, and you put it in your system. Your reasonable expectation would be that that probe will corrode, and you will see metal loss. So you will see that metal, you'll see that metal loss be measured, which would be above 0 on your XY axis. Over time, you'll see, 0 point something, all the way through the span of the probe up till it reaches its limit. You'll see that trend. The reality is the probe will move, up and down the data. You will move, flat. You will move in high gradients. You will sometimes see, like, if anyone's ever had to have their heart monitored or a strict medical to go offshore, you see some stress on your heart, you'll see that EKG bumping up and down. What you got there is differences in that, what that exposed element sees. Now, when you have conductive material, which we used to call conductive scale, but scale's not really the right way to classify it. When that forms on the element, it affects the mass of the element, which affects the resistance value, which affects the metal loss calculated. So you can see it dip into negative corrosion, which is because of a metal gain. That's the most common cause, and that's something that's valuable and that you want to measure and you want to be aware of, because at some point, if the probe is functioning and it's not a fault from the probe, so it is possible to short the probe out, or the probe may have been damaged on installation, where from the probe connections to the unit you're measuring with, there could be a pin damaged or twisted, you know. Any of the people on here who have used probe adapters and ER probes will know if you do it in the wrong sequence, it's very easy to destroy the probe connection. But very commonly, that would be the cause of a negative value.
Thank you, Tommy. The next question is from RB Ortiz. What considerations should be taken into account for the installation of new access facilities in a new line that transports multi-phase fluids?
Good question. So you want to like go to the start of what I've presented and work your way through that and see, you know, where like what you have present from the stuff I've listed. So where you have multi-phase fluids, that's one piece of the puzzle. So what temperature are you operating at? What are your flow rates? What is the pipe material constructed of? You know, do you have potential for, you know, gas content? What are your expected pHs? Do you have a plan to treat the system? That will, you know, basically in a nutshell, internal corrosion monitoring is conceived to, you know, measure and, you know, sometimes quantify your internal corrosion, but really you're testing your mitigation, you know, like you're not testing it, but you're trying to see if it works, you know. Is what you think you're doing to the pipeline working for the probe? Is it working for, you know, is the probe showing very low corrosion rates? Is the coupon showing very low corrosion rates? Is there no localized corrosion? Do you have no sessile bacteria on your devices? That kind of thing. That's the best way I can answer that. But does that help?
Okay. Another question from Aman Rizan is, how do you think intrusive probe will be relevant in the next 5 years, or will the non-intrusive sensors replacing all the intrusive monitoring locations?
No, I don't. I mean, since I started in the industry, people have been asking me that question. It's a very valid question and it's a great question, but neither system's designed to replace the other, to be honest. Anyone who tells you that is, you know, has a motive outside of, you know, science. The techniques complement each other, and unfortunately the non-intrusive techniques have not really ever quite caught up in terms of, you know, how you know, the scales and levels to which you can measure with internal devices. Now, obviously, you know, there's a risk involved with the execution of those tasks, but like any hazard, you can mitigate that by using the proper equipment and the proper people. And I would say that non-intrusive technology is very welcome, in my opinion. I've never came across one that I liked more than the other or found more effective, but they have a place in the industry, and I would say that they should complement each other rather than one try and replace the other, if that makes sense.
Okay, one last question from Ashraf. How do we analyze the polymer coupon, and how does the results gain affects the pipeline?
Yeah, polymer coupons. I've not seen a polymer coupon for a long time. The last time I seen one of them was when I worked in Australia. So the idea of a polymer coupon, you know, in my experience, and I'm by no means a subject matter expert on those, but in my experience, those are designed to simulate what, you know, a similar material that may be subsea or difficult to access is experiencing from production. So when I worked in Australia, those polymer coupons we dealt with were used to simulate the subsea umbilicals, tying the wellheads basically up to the FPSO, and those were not analyzed the same way, obviously, as a mechanical coupon. They would be retrieved and they're positioned on the top side as well. It's very, I mean, in my experience, it's almost impossible to deploy them downhole. But I mean, it's possible, but not that effective. You pull them and you send them to, a lab with the ability to tell you what, has that polymer degraded? Is it in the same condition as like a sample specimen for comparison? You're looking for a change in the material, and you can usually make educated decisions based on what you see from that analysis as to what is causing that. And that can be, I mean, that's basically what the polymer is exposed to. So that's normally how you analyze them. They're usually pulled and compared to an unexposed specimen by a lab, and they will do microscopic, they will do, material testing on it, and they'll see if it's changed in any kind of way. The ones I had seen, they're usually interested in something that would change the material in a way that it may fail. So has it become brittle? Does it stretch more easily than it used to? Has it thinned? Those types of scenarios.
Tommy, maybe just one last question.
I mean, you can ask as many questions as you want, guys. Anybody that needs to go can go. I'm free to talk. Like, it's already 2 a.m., so I'm not going to sleep anytime soon. So I'm happy to answer that question about the ER probe. I just realized that I can see the chat. Yeah, okay, that's a very, very good question. And I've had this conversation a lot. It's an opinion, what I can tell you based on experience. So up until a certain time in the industry, it was considered that because of, a common byproduct of a sour system is an iron sulfide scale. And that would form on the probe, which did what I explained earlier, where it would change the mass of the probe element, and it would affect in effectively what people would consider a negative way, and you would see negative corrosion rates, which is effectively metal gain, which the probe can't repair itself, but you have that metal gain. Also, there was a theory that the probe would short out, because it would, the element would be connected to the body of the probe. So the bodies of the probes are generally 316L, and the elements are usually 1018 or 1010 carbon steel, and that they would have this, metallic bridging between the two, which would short the probe readings out. I've never seen a probe do that, no matter what the element type was. Most commonly in the industry, you'll have a pig nose style element, or a little strip element, which has a smaller surface area, but is positioned centrally, so much further away from the edges of the probe, and can't effectively short itself. But in my experience, working in some very sour facilities in the Middle East, offshore UK, and definitely Alberta, yes, it's a valuable tool, but you need to know how to use it. You need to accept that you will see those ups and downs on the metal loss and the metal gain, and you have to watch for those trends, and you have to understand. Basically, if you think about it this way, if iron sulfide scale was completely stable, we would, in a sour system, we would have a very, very, very low chance of internal corrosion failure, because that scale would completely coat the internals of the pipe and passivate it, so effectively protect it from, electrochemical change. Reality of life and hydrocarbon production and, dynamic systems where, the price of oil is is low, so production is slower. Our price of oil is high, so you may be going full speed, or conversely slowing down to maximize the price. The scale doesn't stay intact, and when it forms and then is removed or breaks or is cleared, whatever terminology you want to do, that creates a small anodic area, and the rest of the pipe and infrastructure becomes the cathode. So you want to know when that happens, and an ER probe properly positioned in the line, specified within the environment that I explained at the start, we are looking at the effects of the environment, is an effective tool, in my opinion. But that is not sacrosanct or the gospel from AMPP. It is a matter of opinion, and you will have people who philosophically believe what I do from their experience, and you have people who feel the other way, where they've had ER probes incorrectly positioned and spec'd in a solar system in the wrong spots with poor instrumentation to interpret the data and just got no value from them. And you can't blame those people for thinking they do not add value. So my opinion only, yes, a very valuable tool.
All right, thank you, Tommy. Can I have a request to everyone? Could we just turn on the cameras so that we can do a group photos?
Thank you, Wai-Sing. Can everyone please turn on your video camera for a quick photo session? And just be camera ready. All right, great. 1, 2, 3.
Shafiq fixing his hair. Shafiq, I seen you fixing your hair, buddy.
1, 2, 3.
You're looking good.
Okay. 1, 2, 3, and last one. Okay, thank you. Back to you, Wai-Sing.
Thank you, Tommy, for the great insights and your sharing with all of us here. And thank you, everyone, for attending today's technical talk. We hope to see you again real soon. And maybe we'll do one session when Tommy's in Malaysia, a physical one, yeah?
Yep, I will be in Malaysia towards the end of June. So if anybody wants my details or Mr. Rizwan's information, no, it's confirmed you're not McGregor. I'm too nice to be McGregor. Yeah, if you want my contact details to hook up, or you want to come pick my brain, or you have a challenge I can help you with, feel free to reach out.
All right, thank you, everyone. Have a great day.
Thank you very much for having me. It's a pleasure.
Thank you.
Okay, thank you.
Bye.
Bye-bye.
Have a good day.
Thank you, everybody. Thank you. Thank you.
Thank you, everyone.